Welcome everybody to the 3D scanning and motion capture lecture. As usual, we're going to start with a very quick recap of what we have done so far. So at the beginning of the class, we looked into 3D concepts. We looked at how to obtain 3D from sensors. So we have various sensors such as RGBD, stereo, and so on. And we talked about how to get 3D representation from these ones, and we also talked about what these representations are, such as point clouds, voxels, polygonal meshes, parametric surfaces, implicit surfaces, and so on. We also talked about how to convert between these. For instance, if you have an implicit surface, like a sign distance field, you can run a margin cubes. You can then extract a mesh out of this one, then you can use that mesh in order to render it in the graphics pipeline. We also talked about distance fields, how to raycast them, nearest neighbor lookups, and so on. We also talked about correspondence finding and matching, basically features. Like one of the long-standing challenges in computer vision is to basically establish features between different views. We talked about what do we do with these matches once we have found them. So we talked about these correspondences that we get from multiple images, and we talked about bundle adjustment, how we can use these matches then in order to optimize for the camera poses as well as the 3D points. And this whole process, the structure for motion, maybe as a name clarification, I'm writing here in parentheses structure for motion, but basically structure for motion is correspondence finding plus bundle adjustment. And of course, all the outlier rejection, ransack, and stuff like this. We also talked a little bit about RGBD bundling. We talked about various terms. We're going to talk about these ones a little bit more today. If you haven't fully understood them, I hope today we're going to have a couple of practical examples how we deal with those ones. And we talked about specifically how we can solve these objectives. So specifically, if you have reprojection errors or so, or you have an RGBD bundling feature matching term, that how to solve these ones. So specifically in the last lecture, we talked about nonlinear squares, how these functions can be, or these energy terms can be solved, right? So we talked about various solvers. We talked about Newton's method. We talked about Gauss-Newton that approximates the Hashing with 2 times JTJ. We talked about how to practically solve Gauss-Newton with these linear system tricks instead of inverting a matrix. And finally, we talked about Levenberg-Marquardt, which is probably our solver of choice in many of these problems that we're going to encounter today, and we have encountered already in the previous lectures. Okay, so today we want to go and continue on these lines. So we want to specifically talk about rigid surface tracking and how to do reconstruction. So in the previous lecture, right, we've talked a lot about optimization and so on. And this, in a sense, like follows directly up here. So what do we want to talk about specifically here is we want to talk about frame-to-frame alignment. So in this case, we're assuming we have 2 RGBD frames, right? Maybe let's ignore the RGB part for now. Let's just say we have just 2 depth frames even. And what we would love to talk about today is we want to talk about this frame-to-frame alignment. And what does it mean specifically? Well, if you're looking at this term here, this is what we're going to deal with today. So what we have is we have 2 frames here, and then we have a transformation matrix T between these 2 frames. This matrix has 6 degrees of freedom, so we have 3 for rotation, 3 for translation. That's very common now. What we're going to, basically most of the lecture today, we're going to talk about T having 6 doves, and the question is how to solve these 6 doves. And what I'm assuming here in this frame-to-frame case, that we're going to have a loop here that goes over all the correspondences. And these correspondences are P and Q respectively. This is in the first frame, this is in the second frame, right? And we're just going to sum up over all of these correspondence pairs. And we would love to do is we would love to solve for the T here. That is the matrix that transforms all the points from one frame to all the points in the other frame. Yeah, so, and we're going to talk about how to align these 2 frames. So there's a couple of things that are important here. First of all, obviously, we have to solve these nonlinear terms. That's one part of the problem, but we also have to establish these correspondences P and Q. And there's a lot of, intricate details that we have to talk about. And one of the methods we're going to specifically talk about is ICP. I have mentioned this already a couple of times, probably without explaining it, but the thing is, like, ICP is such a popular method that, you know, if you're in this field for a couple of times, you will just mention it. So ICP is short for iterative closest points, and this is what we're going to talk about today a little bit. Okay, so let's talk a bit about more again about the problem setup. So part of it I've already mentioned. So here we're going to talk, I mean, I'm calling it RGBD tracking, but what I really mean is actually looking into the depth alignment between two frames. So given an RGBD camera, right, the goal, what we want to do is we want to be able to move this camera around in space, and we want to know relative transformation matrices to these camera positions where you are. And this is an analog statement to saying, like, give me 2 point cloud, find the rigid transformation between those point cloud, right? And this is actually the same thing, right? So, like, do the point clouds move between frames, or does the camera move? Is analog, like, this is all relative, right? So you don't know which one is doing it, but in practice we're assuming that our global scene representation lives in a global coordinate frame, and what we're assuming is that the camera basically moves around, and our goal is to find the camera transformation matrices, the poses respectively, that projects every frame coordinate system into this global scene coordinate system. Okay, yeah, and in a sense, what this means in practice is, right, if you're saying we have two frames here, right, let's say these are 2 frames from a depth camera, I mean, this is a laser scanner in this case, but let's say we have these 2 frames, frame 0 and frame 1, and like, solving these 2 problems is essentially the same thing as saying, well, let's minimize the distance between the 2 implicit functions of these points, right? So the points, in a sense, they give you a low order approximation of the surface. Could be first order, could be 0th order, could be second order, depending on what kind of approximation you're using. And the idea is that basically you can try to optimize the distance such that it's minimal between these 2 frames when you're having correspondences. This could be an implicit function like a TSDF, but it could be also, you know, whatever other approximation we're doing. And then what we want to do is we want to find this transformation matrix that aligns these 2 frames with respect to each other. Okay, and this is the thing what I already mentioned now. Like, the idea is that we're going to use this ICP method, this iterative closest points. And the high-level overview between ICP, so ICP is basically this problem statement, right? So we have these 2 point clouds, and we're trying to find a transformation between these 2 points. And the ICP has this high-level overview where you're first starting to find some correspondences. Once you're having correspondences, you're having some form of, like, outlier removal pruning. Then you have some optimization based on the correspondences you found. So you're getting an initial transformation T based on the correspondences you found that is optimal relative to these found correspondences. And then you iterate. And the high-level core idea of an ICP now is that this data association, this correspondence search, is imperfect. So if you had perfect correspondences between 2 depth frames, or between 2 point clouds, you could solve in one shot the right transformation and the right rotation, translation rotation. But in practice, you don't have that. So the ICP is a way of saying, well, how can we deal with that we don't have accurate correspondences? And the idea is this iterative process, right? So, and this is like why you have to redo it all the time, right? So we first have this data association, and based on that, we're doing then the optimization, and then we iterating, finding new correspondences, and we continue this process until things converge. To illustrate the problem here again, right? If you want to align 2 point clouds, right? Let's say these are the red curve here and the green the blue curve here are our point clouds. And if we having known correspondences between those 2, so if you know this point matches to here, this point matches to here, this point to here, this point to here, this point to here, in that case, we can find the correct rotation and translation in one shot. This is a Procrast algorithm, and this is relatively straightforward to do. You have these points, you compute the covariance matrix, and then the SVD of this covariance matrix gives you the rotation. And then you can align them accordingly, right? But the big question is basically, how do you find these correspondences? And this is where the Icp method comes in. So I explained already briefly this high-level concept. So the idea is we're just cheating a little bit on the correspondence finding. We're saying, well, we don't know the exact correspondence, but we just assume that the closest point in the respective other point cloud, that's the correspondence. So if I have this point here on the red curve, I'm just going to try to find in this blue curve, oh, this is my closest point. All right, so this is a correspondence. From here, this is the closest point. From here, this is the closest point, and so on, right? And of course, this is not perfectly true, right? So these correspondences, they are not actually ground truth correspondence. They're just nearest neighbor correspondences. But the idea behind this iterative closest points algorithm is we just say, well, this is good enough to get an initial alignment. And then what we do is we just iterate and find a better alignment. And we just continue this process until we are close enough, right? So we find nearest neighbor correspondences, then we're computing a relative transformation based on these nearest neighbor correspondences. We get a little bit closer, then we're finding new correspondences, and these new correspondences are supposed to be better now because we already have a better initialization from the previous iteration, right? So now here the nearest neighbors are already much better, for instance, than they were in the previous slide, right? If we go back here, right, these are very far away, so these are not so good, but they might be good enough to get an initial alignment. This is this alignment here, and then you just find new correspondences, you optimize again, and so on. And this is an iterative process. This is why it's called iterative closest points. Okay, so this is the basic high-level idea of an ICP. In practice, there's of course, it's a little bit more complicated, but the idea still stands what I just described. So if you're talking about the basic ICP algorithm, right? So we're selecting a bunch of random points in the source frame. Let's say we have a point cloud, right? Let's say we're selecting 1,000 points. For each of these 1,000 points, we're trying to find matches. So we're matching each other point to the closest, to the respective closest point in the other scan. So we're finding these nearest neighbors. For that, we can use efficient search structures like a KD tree. If you have to implement this yourself, you're probably going to use some sort of library like ANN of LAN. Nan of LAN is also a good thing. LAN is like this one header that does everything in one header. You can use those ones to find the nearest neighbor matches. And then we do a little bit of outlier rejection. So we're trying to find, oh, maybe some of these correspondences that we found, they were too far away, or their surface normals was too different. And we reject those. Like distance is a very common rejection criterion here. For instance, if it's greater than k times the median or something like this, right? So you're rejecting basically the outliers. And then what we're doing is we're having this error function here that goes over all the correspondence pairs P and Q, when we're optimizing for the rotation and the translation respectively. Yeah, there's actually a linear closed form solution where we can analytically solve it, but more to this later, right? But this is the high level part of the ICP. So we select a bunch of random points in the source point cloud. We find nearest neighbor matches in the target point cloud. We do a bit of outlier rejections, and then we are solving this function that gives us RNT for the current iteration of the ICP, and then we're just iterating and finding new correspondences, right? So we have this selection of source points, matching, we do weighting of correspondences and rejection of correspondences, and then we're finding the current transform based on the error matrix, and then we iterate this whole thing, right? And this thing continues, and to state the obvious probably already, you have to be close enough right at the beginning to find some correspondences, because if you don't find anything right at the beginning, an ICP wouldn't work. And we'll talk about this one a little bit later to see when and when not the ICP works and when it doesn't, and how to possibly fix it and what we can do. Okay, so let's talk a little bit about it. So I want to talk about these different things here a little bit in more detail. And already a fair warning, there's a lot of different ICP variations. So ICP is just such a fundamental method in geometry processing, in RGBD scanning. And there's a lot of different versions of it. And we're going to talk a little bit about a couple of criteria here. So we're going to talk about speed, stability, tolerance with respect to noise and outliers, the maximum initial misalignment, right? What I mentioned is if you're too far away right at the beginning, then you can't have any correspondence to get started with, and so on, right? And there's a very cool survey actually of this. I can recommend this one. There's a comparison of many Icp variants. It's already a little bit of an older paper from Simon Rusinkiewicz and Mark Levoy. This is a good overview what was kind of a thing in 2001. This still holds for the most part. I mean, there's a few new methods coming out right now, but they talk mostly about like stability and robustness, like for instance, like how noisy the point clouds are, and then what Icp variant performs how well and so on. Okay, but as promised, we would like to talk a little bit more into detail about the Icp variations. And about these things, what I just mentioned, and I would like to start with the selection of these source points. And interestingly enough, that is already pretty important. So how do we select source points? Well, I mean, a simplest thing could be I'm just going to use all points, right? You could do that, but that possibly could be slow. It could also be that this is not a good distribution of points to find. And I'll talk to this in a second, what this means, that maybe a subset of the points might be better conditioned than using all points. Another thing what you can do is you can just do uniform subsampling, meaning that, okay, we don't take all points anymore, we just take a subset of these points. We can do random subsampling, right, to select a random set of points. Or we can do some sort of stable subsampling. This Gelfand paper here is pretty interesting. So basically select samples that constrain all degrees of freedom of rigid body transformations. So in practice, what that means, I want to talk about this latter part a little bit because this illustrates the problem. So if you're going to go ahead and have two surfaces here, right, or 2 point clouds, right, and you want to align these 2 point clouds, if you're just going to do some uniform sampling, right, we're just going to sample points here on this red curve in a uniformly spaced fashion. And then for these points, we're going to find our nearest neighbors for our Icp. And what you can already see here is here is actually a lot of geometric detail. So this geometric detail, in this case, we didn't sample, or well, barely sampled it at least, right? Or here in the target point clouds, we don't even hit anything there. And the question is, why is that a problem? Well, what we would love to do now is we would love to take these points and use those matches with respect to the other surface and then computing a translation and a rotation matrix. Now, if you're going back here, so what I mean by that constrains all degrees of freedom of rigid body transformation. So one common way when this fails is when you just have 2 planes. So if you have 2 planes and you want to align 2 planes to each other, the planes can slide. The error is 0 in the alignment, but there's multiple solutions for that. And that's a big problem. That means that geometrically speaking, the degrees of freedom of the rigid body transformation would be under-constrained. And this is essentially what would happen here too. So basically, this is these points almost lie all on a plane here. And because they lie all on the plane, the resulting transformations that you're getting is going to be under-constrained and is ambiguous. So you can have multiple transformations that explain these correspondences. And in order to avoid that issue, what you do is you want to capture a lot of geometric detail. So the more geometric detail and more geometric variation you have, the more you're over-constraining this, this rigid body transformation, right? So in this case, what we would love to do is we would actually love to go ahead and sample this part here much, much more, right? So I'm not going to go into detail how exactly to select it, but basically what you can do is you just look at the variation locally on the surface and see, oh, no, we have a lot of variation in these regions. For instance, just look at the normal also. And based on that, we just distribute more samples in regions where we have kind of non-planar surface parts, right? And in this case, we don't just align 2 planes anymore, but in this case, we're having a lot of samples that are actually aligned, that are finding geometric variation. And because of that geometric variation, we can find better transformations between those 2 points. Now, what's also interesting is maybe to say, at the beginning, I mentioned, well, why don't we just use all points? I mean, obviously, speed reasons could be one thing, especially when you have big point clouds. But there's another thing what's interesting. So if most of your points are actually here on a plane, and you only have a few points that are on the geometric detail, that would mean the resulting optimization problem is not very well conditioned, right? So most of the things can basically say, oh, slide, 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 and just a few of them constrain it. So it might be better to have fewer samples on the planar regions, but rather have more samples in the regions with higher geometric variation. And that is something that is quite important when it comes to numerical stability, especially when you have big point clouds from, let's say, laser scanners, where you have millions or even billions of points, and when you align them, then the sampling actually makes a big difference, not just from a speed perspective, but also from a perspective of numerical stability when you're solving the systems afterwards. Okay, now let's say we've selected a bunch of these points now. Now we want to go ahead and match those points with other scans. And the matching has a couple of things, and basically the weighting and the rejection here is part of the matching. And there's a lot of literature to that. This is actually a fairly, well, it's a fairly tricky thing to do it, right? Because you might accidentally, like, you're just trying to find a nearest neighbor, but your nearest neighbor might accidentally be not the right nearest neighbor, right? And that is something we have to think about, like how can we address these kind of issues, right? So that's something we want to talk about a little bit in more detail. So one of the big things, already mentioned it, right? Closest points often are bad corresponding points because they just match to something that is just not the right thing. And the point right now is how can we find better matches? And there's in principle a couple of ideas. So what we want to do is we want to improve the matching effectiveness by restricting it to compatible points. And what does compatible means? Now we're going a little bit back to kind of what we've been talking about for stereo matching. Essentially what we're trying to do is we're trying to engineer some low-level features that are fast to compute that tell us whether 2 points are matching or not, based on the color, based on the geometry, and so on. So the simplest thing you can do is you can just look at the color values around it. Color values, well, could be straightforward. You just check literally the color value at this point. You could also go ahead and check the color neighborhood, right? You can do some sort of sum of squared distances of the colors. You could even go more crazy. You could even say, oh, we're going to compute a sift feature for every point here, and then we're finding which one is better based on the current sift descriptors. And that works, but it's already super slow, right? Then you have to compute a sift descriptor for every point. So there's basically a bit of a trade-off here, like how much time and effort in compute do you want to spend to verify that a nearest point match is compatible or whether it's incompatible. So you can do this on colors. In principle, you can use all kind of color matches or color features, but be aware that, you know, if you're using actual feature descriptors such as sift here, you can do that. But in practice, nobody does it because it's way too expensive to compute. And actually, often when we're talking about point cloud alignments, we don't even have color, so we might not be able to use that. So what are the other options we can use? We can use the normal variation. Normal variation is a very, very, very good feature because that's straightforward to compute, right? We check for every point what the surface normal is, and then when we try to find a match, we check, oh, our normal doesn't work, and so on. So that's a good thing. But then there's other possibilities like curvature, higher order derivatives, other local features, stuff like this. So in principle, what we're talking about here, it's actually a feature matching problem, right? So when we're trying to find closest compatible points, we're trying to find points that are close from a physical perspective in 3D space, and based on that you can compute various types of features. For the most part, people use very simple approximations. To be precise, I'm going to go quickly to these middle 2 points here. So what people are doing, for the most part, if you're talking about an ICP without RGB information, and you're just doing it based on the distance values, so you say distance between the values that you found and so on, is greater away than, let's say, 10 centimeters, and then you have variation of the normals. Let's say you have to be within 30 degrees of difference when you're trying to find these correspondences. Okay, when we're doing the data association itself, a few things we've mentioned already. You can use the nearest neighbors, and then approximate nearest neighbors, flan, nanoflan. These are good tool sets that you can use. There's one thing what we haven't talked about is there's one way to find good correspondences very fast and efficiently. And that is specific to RGBD cases. So if you have two RGBD frames or two depth frames, what you can do is you can simply go ahead and project the points from one frame with the initial transformation into the respective other frame. And if you're doing that, this gives you a correspondence. This is not a nearest neighbor correspondence in Euclidean space, but it's a nearest neighbor in projective space. And I'm going to call those, or the literature calls those, projective correspondences. So this is not always possible, right? So you need some sort of structured data, depth images. This works. For raw point clouds, it doesn't. But often these projective correspondences, they have some nice properties to make an ICP work very well. And it's actually really fast to compute, right? So you don't have to pre-compute like a approximate nearest neighbor data structure like a KD tree or whatsoever, but instead you can just use these correspondences, and this is super fast to do. Another thing you can do is you can do pruning based on correspondence to borders, right? So basically you can say, oh, if it's on the edge of the scan, you don't use it and stuff like this. But this pruning and the rejection of outliers is actually quite critical. If you don't do this at all, probably ICP won't converge because you just have a few wrong correspondences, and since this is an L2 term, when you're solving for the error metrics afterwards, a few outliers can kill you. So you really want to make sure that you don't have any, well, you don't have any, at least you don't have gross outliers in it. And again, I wanted to illustrate this here again, right? We have here these two curves. You have this red curve. So what you do here is if you find, for instance, this point matching with this point, then you're comparing this normal with that normal, and these two normals here are very different, which means that these correspondences are probably not that great. But if you do this, this is fairly easy to implement, and it gives actually quite good results in terms of the actual alignment. So I think there's a very nice way to address these kind of things. Okay, now let's talk a little bit about the assignments of the error metrics. And this is something we haven't talked too much. I mean, all what we have been doing is we have said, okay, let's find some matches, and then we're trying to minimize the distance between the matches in the source and the target point clouds, right? And in practice, what that means, it's actually called a point-to-point error, what we have talked about, right? So we're having 2 points in the source and the target points. We have correspondence between those, and we're trying to minimize the distance between those two. But there's a few variations of an ICP which improves upon this metric, right? And one of this improvement is a point-to-plane metric, right? So instead of finding direct nearest neighbors, you're finding nearest neighbors with respect to the normal of the points, right? So basically what this means is if we have a point P here in the source point, right? This point P here we want to project this point P here onto the plane of Q, right? So we're projecting this point here. So we're saying, oh, this is the nearest neighbor, but instead of trying to minimize that distance, we're trying to minimize the point to plane distance, which is this one here. And the advantage here is if we're using the normal of Q here, this would mean that the surface can basically, or the alignment between P and Q, they can slide along here, right? And this sliding along the planes is actually quite useful because in practice, you don't know whether P matches here, here, or here. Essentially what we're doing here is we're having a first order approximation of the surface, and we're kind of letting the correspondences slide across this first order approximation of the surface instead of having a nearest neighbor approximation, right? And this is like, I want to illustrate this very quickly what this point-to-point versus point-to-plane means, right? So again, point-to-point is everything we have been talking about so far, but now we want to talk about this point-to-plane a little bit. So basically, instead of assigning this point with that point, you would say assign this point with that surface here, which is given by the normal of this closest point, right? So you still, the correspondence search is still the same. So you're still finding the closest point, but then instead of trying to minimize the distance between these 2 points, you now compute the point here, and based on this point, you optimize, you get the normal, and then you're optimizing the projection on this plane that is given by the normal here. And this is significantly better because now we can basically, if you have 2 planes, we allow the sliding across the planes. And as mentioned, right, like we still need to have enough geometric detail. But the problem is basically if you have like a little bump, and I want to quickly let me go quickly back to this case here. So this is a good case here, right? This has one bump here, but this point matches here, or this point matches here or here. That one you don't know, right? So you want to make it slide everywhere except where you have the geometric variation that over constrains it. And in cases like these ones here, the point-to-plane metric will be significantly better because it allows the sliding of this geometric detail to match eventually, rather than going ahead and just making a greedy association here. Okay, so this is point-to-plane, and point-to-plane is pretty much the standard what people are doing. Often people have a combination of the two. So sometimes you have a term that is like 0.1 of point-to-point weight and 0.9 of point-to-plane weight. This is what I often used in my own implementations. Okay, so how do we minimize the whole thing? It's a little bit closely related to what we have learned in the last lectures. For an ICP, there's a few tricks you can do. One trick, so first of all, let's look at the error function. So this is the point-to-plane error function. Again, just to clarify, for an error function, this point-to-plane is straightforward. All you have to do, you take the normal in the target point cloud, so Qi and Ni correspond to each other, and just have a dot product with this difference vector here and the normal here. Right? So if I didn't have this dot product with the normal here, this part here in the middle would be just point-to-point. Right? You just say P has to be close to Q, but now P has to be close to Q dot producted with the normal, meaning that you're computing this point-to-plane distance. Right? So it's very straightforward actually. To implement this point-to-plane metric, but it makes the optimization a little bit more challenging, because while for the point-to-point one, there's this closed form solution, like Procrust, for instance, right? There's unfortunately no closed form solution anymore when you have this dot product with the normal. But there's a few tricks what you can do. One simple thing what a lot of people are doing, they just say linearize the rotation angles. So you just say, well, sinus theta is equal to theta and cosine theta is equal to 1. All right? So this one is basically saying this one is basically saying that, okay, we can linearize these angles here. And now what you can do basically is you can just say, oh, if this was linear in the rotation, you can just multiply, or you can just put this dot product of the normal in here, and then you have this approximative function here that you're getting, and that now becomes a linear system. And this linear system you can actually solve with a linear solver, right? And essentially, when you're putting all of these constraints here in this linear system together, you're ending up with a matrix that looks like these ones here. So here we're having this is basically the points times cross-producted with the respective normals here. You have the normals here. You have the x is going to be your rotation and the translation unknown. So you have 6 here, 6 unknowns here. And here we have the respective residual terms. So this is nothing else but rewriting this formula such that we're getting rotation and translation as an unknown vector, right? So we have here these unknown vectors. But since we linearize those ones right now, we can write those as a linear matrix. A times x is equal to b. And then we can simply use our least square solvers, what we've talked about in the last lecture, and we can try to solve those ones. Now, obviously, one thing that is very important here, if you're talking about these matrices here, so x here, the dimensionality of x here is pretty clear. That's a 6-dimensional vector. That's our unknowns, right? A and B, A is doing nothing else for each row here. You multiply it with respect to these variables here, right? This is basically just multiplying all this stuff here with the respective unknown variables here, right? So A has 6 columns, where each column is multiplied with one of the unknowns here, or with one of the unknown channels here. And in terms of the number of rows of A, the number of rows is equivalent to the number of correspondences you're going to get, right? So if you're having a depth map with like hundreds of thousands of points, then you would have hundreds of thousands of entries possibly in A, as long as they were not rejected in the outlier pruning, right? So A is a pretty large matrix. So A is like something like, it's basically number of correspondences times 6, where 6 is the number of unknowns. This B vector, same thing, right? So the B part is basically the stuff that is the residual here that is left over. And B is a residual vector, and the vector has number of correspondence unknowns, right? So like for every correspondence here, you're going to get one entry in B, one residual term for B. And since this is an over-constrained linear system, we have to use a least square solution. So we're using the normal equation here, meaning that we're multiplying A with AT and B also with AT, right? And as a result here, AT is a 6 times 6 matrix, which makes sense, right? And ATB is also a 6-dimensional vector now, right? So this is a 6 times 6 linear system that you can solve actually also in one shot now. But be aware, solving this system here is not solving the original error function, because we just linearized the rotation angles here, right? And that's important. So this is important, that we don't just linearize. Sorry, we have to do this multiple times basically, right? So okay, and this is straightforward then to solve, because this is just a 6 times 6 linear system. You can use whatever favorite SVD or whatever solver you have and can solve that then directly. But you have to be aware that you have to do this a couple of times, because this is a linearized version of the original equation. Okay, so there's some literature to it, and this is also what I'm going to give you later as homework to look at. This is linearized point-to-plane literature, is this Love paper. This only holds for small rotations, but in practice, if you do frame-to-frame ICP, this works. So it's basically a linear approximation of the rotations, and they have a nice deduction and derivation of how to get there. So this is something I want you to look at. I'll provide the link later on at the end of the slide deck. Okay. There's another option. One option is to ignore this whole linearization stuff. One option is to just use Levenberg-Marquardt. It's a second-order method. It has quadratic convergence. It rules them all, and it works great. Right? So you can just go ahead and have this E frame-to-frame with your point-to-plane terms. You can just use LM to solve that as well. That's also perfectly fine. It's possible. I wanted to mention this linearization trick here because this is something a lot of people do, especially when they implement stuff on the GPU, because it's relatively it's very easy to parallelize this part. This one is also doable to parallelize, but it's a little bit more complicated to implement. Anyway, but this one should be clear to you right now, right? This is a least squares problem, and we can use our favorite solver, in this case LM. We get quadratic convergence. This is great, and you can solve it this way. Okay, so this is the standard ICP, right? So we have now seen a couple of things here. I want to recap those very quickly. So what we can do is we first find correspondences. We know how to find those by nearest neighbor search, right? By ANN, FLAN, NanoFLAN, or whatsoever. We have some correspondence outliers detection, like we're using, for instance, the surface normals. We're using the distance, and so on. And then we have an error metric, and based on this error metric, we solve it, and the solving can be done with some sort of linearization, or it can be just done with LM. Okay, and that's basically the ICP, right? But there's a few things more to it, how to make this a little bit more efficient. If you remember in the last lecture, when we talked about optimization, there's often these coarse-to-fine and hierarchical approaches in optimizations. This is something people using here as well for an ICP, for instance. So, for instance, if we have two depth maps, these are two frames from a Kinect, and if you want to align those two, you can go ahead and start at a lower resolution depth map, for instance, and then go to a finer level. And the idea here is, well, the lower resolution depth maps get you close enough to give you good initialization for the finer levels, where you can get then a finer scale alignment in the end of the day, right? And this coarse-to-fine thing is a thing people do. Sometimes they call it pyramid optimization too. But this is a thing that is often being done, right? And yeah, so the idea is essentially, while we're optimizing in a lower resolution here first, we propagate the solutions to a finer level, and then we're running another ICP on the finer level, right? And we're starting on a low resolution depth map, then go to finer levels. And as a result, what we're getting here is we're getting faster convergence And we're also avoiding local minima. We're avoiding downsampling and smoothing. And in practice, what this means is that you're basically getting more faster motions. And faster motions eventually means that your ICP works in more cases. And when we're talking about RGBD reconstruction, and you've implemented one of these like Icp methods or so on, you will see that it's sometimes, you know, like the core thing of getting such a system running is to having a good Icp version that has a large basin of convergence that allows you to move the camera around fast enough, right? Okay, so let's conclude on the Icp here. So because the correspondence finding is not differentiable, there's a lot of hacks of like alternating this kind of things, right? Because ideally what you would like to do is you would like to just find a differentiation between two aligned surfaces. And yeah, because of that, you have to do some alternating schemes, and this is basically what Icp is doing. Continuous surface approximations is not so easy to find. That's why this differentiable version is not so easy. There's a few people who tried to do this by, you know, sampling and then differentiating through it. Not so straightforward though. Might be some cool stuff for related work. That's also very related what people do with neural networks right now in deep learning. So that's something maybe to keep in mind there. There's many Icp variations. Adding color terms. Features in color terms. Yeah, I can do similar algorithm for RGB only alignment in principle when you have to estimate the depth somehow. And there's also, more recently, there's like symmetric Icp variations from Rosenkiewicz 2019. There's a cool idea basically of when you're saying you have a point to plane distance between P and Q, you can take the average normal of both of them together, which is kind of interesting, and that's shown to work better. This is also one of the papers I will give you as reading homework, and hopefully that gives you also a bit of a better overview of what can be done in these cases. Okay, so this is Icp. This is basically, it's a very fundamental method for aligning two point clouds or two depth maps to each other. And now we want to go a step further though. Now we want to take the alignments and we want to do actual 3D reconstruction. And for the 3D reconstruction, essentially, I'm going to start with a very simple method, right? We've talked a little bit about this Hoppe method already, about how to triangulate it. But now we want to talk of reconstruction in the context of implicit functions like sign distance fields. We also talked about Poisson surface reconstruction, but now we want to have another version of this where we're doing sign distance field integration. And the idea is that these kind of methods we're going to talk about right now, they are mostly real-time methods. So this kind of stuff can be done extremely fast, actually. So the idea here is, what you want to do is you want to compute poses between frames, like with an Icp. We want to take those poses and integrate the data, in this case the depth data or the point cloud data, into a shared model, into a distance field. And as we're getting more and more frames, we want to update this model essentially on the fly. And when we're done and we have all the frames accumulated, then we can extract the mesh with marching cubes, for instance, from this implicit representation. Now, there's one thing what I haven't mentioned yet. So when we're talking about Icp, for the most part, we're talking about Icp between two frames. One thing that is kind of nice, you can also do, this is called frame-to-frame Icp. But there's also a thing called frame-to-model Icp, which is basically taking this shared model that where you integrate all the data in, and use that one as a reference where you align new frames to it. And this is something we're going to do here for the most part, because for the shared model, you're basically getting better normal approximations, and then point-to-plane Icp work better. Okay, so let's maybe quickly recap. So we've talked already a little bit about distance fields, right? Specifically about sign distance fields. And what we know about sign distance fields, we have this grid, right? So let's say this is our fancy grid here. This green thing here in the middle is our surface. And now what we have is we're having values in each of these grid cells that tell us how far each grid cell or each center of a grid cell is away from the surface, right? So for instance, if you're on the surface, you would write a 0 in it. But if you're like one voxel away, you would write a 1 in it. If you are in the interior here, you would have -1 in it. This is the sign, right? Outside here is 1, and inside here is -1. And the further you go away, the larger distances go. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So this is not perfectly accurate what I've drawn here. In principle, you of course this is like not 1 away, but it's like the square root of 3 away actually in 3D, right? Because it's like in 2D it would be square root of 2 away. But since I was too lazy to draw this, I just made the simplified version of the sign distance field. But I hope you can extrapolate from that, and you can imagine that these are accurate distances from the surface away. So this is relatively clear. This is our distance field. And now we also have this concept of a truncated distance field, truncated sign distance field. Truncated sign distance field, similar idea, except that you just truncate the stuff at some point. So everything that is greater than 1, for instance, we're just going to truncate. What I've done here is not perfectly accurate. In what you really want to write here is not available, but in principle, for this truncated sign distance field, you also want to write you just want to propagate the largest distance value. And this largest distance value in a truncated sign distance field is the truncation, right? So the TSDF has a truncation. In this case, the truncation is set to 1. So everything out here would be also initialized with 1. And the same thing counts here for the interior. Everything here would be also -1, right? Okay, so I think this is pretty clear based on what we already know. We should know what the distance field is doing. We should know how it's stored. And now what we don't know yet is how do we compute the distance field from a series of depth maps. So now what we're assuming in this problem statement is we are assuming that we're getting as input a depth map, and we know the pose, meaning the rotation and translation, from the camera position of this depth map relative to the global grid. So for instance, we ran an ICP, and this ICP gave us this camera transformation that tells us the pose of our camera. So this is our camera here, it's a fancy camera. This is our grid, which stores the sign distance field, and this is our hypothetical surface, which we want to reconstruct. And this is a process called volumetric fusion. Volumetric fusion is a method that basically now takes these depth maps incrementally and fuses them into the voxel grid in order to compute this sign distance field, a truncated sign distance field. Okay, and this part of this process here is called surface integration. And in the surface integration, what you do, you imagine, oh, there's a ray, and on this ray you observe basically a distance value. This is what your depth map has observed, right? So your depth map observed a distance value here, and in this distance value, you know how far that point along this ray was away from the camera, okay? And what you're doing right now is you're going ahead and projecting every voxel here along this ray into this point, and now you're just checking how far is each voxel away from the respective depth point that we observed here, right? So if the surface is here, the depth value would be roughly here. So we would know this voxel is 1 away, this voxel is 2 away, this voxel is 3 away. This one would be 4 away, 5 away, 6 away, 7 away, 8 away, right? And so on. So this is in front of the surface here, and you measure the distance, how far this is away, right? You're doing the same in the other direction. What's behind the surface, you do the same thing, except that you're assigning negative values to it. So here we're assigning -1, -2, -3, because these are the distances of these voxels relative to this depth value. And what you can already see here is, if I'm going quickly back here, this sign here referred to inside the surface, but this is not true here anymore. Now the sign has a slightly different meaning. In this case, the sign means in front of the surface if it's positive, and if it's negative, then it means it's behind the surface, right? That's all the sign is doing here. This does not mean that it's inside or outside the surface. In this case, it just means it's in front or behind the surface. Okay, and now all we're doing is we're doing this basically for every ray here. Now let's take another ray, right? So this ray here, these voxels here project into this pixel. We know the depth value, we assign the respective sign distance values. And we do this for everything, right? And we're just computing the distance field respectively, based on this one depth image that we have seen from this pose, right? So the relatively straightforward process. So algorithmically, what you have to do here is you have to basically project every voxel in this grid into the depth map. You check in which depth value you're landing, and based on the depth value, you're assigning a distance value to the respective voxel. This is the surface integration part. Right. And if we're doing this, we're getting something that looks like this. Eventually we get our signed distance field. And one thing I haven't mentioned here yet is the truncation. So at some point you truncate the whole thing and say everything beyond a certain value, you're just assigning a 1 to it. Right. Okay. Right. So what we have done right now is we have taken a single camera. Right. This single camera has a bunch of rays. We can use those rays to compute signed distance values for each voxel. And this camera also has a pose T1. But now we're getting different cameras. So let's say we have another camera, and this camera is here. So this camera has pose T2. Again, we get the poses from our ICP. And this camera also shoots a bunch of rays, right? And we have a third camera. This one here also shoots a bunch of rays, right? And now the thing is, let me go back one, and let's say we only have 2 here. Now we're going to have a bunch of voxels that basically are seen by 2 cameras. So for instance, this point here is seen by this camera, and this point here, or this voxel here, is seen by that camera, right? And now what we want to do is, we have just seen the surface integration. Now we're just doing surface integration for each of them, and we're computing the average of it, right? So we're taking the average distance of all of these ones, and that basically computes the average signed distance between all the depth values that have seen a certain voxel, right? And we can have many of them, right? So we can have, in this case, we have 3, but not every voxel is seen by the 3. Just some voxels are seen by the 3. And one way to do this is we literally compute a signed distance grid for each of the cameras independently, and then at the end of the day, we merge it. But this would be computationally a little bit efficient. The nice thing about this method is you can incrementally fuse that by computing a weighted average, right? So the way this works in practice is, so each of these formulas here, they're relative with respect to a single voxel. So if you have the distance value in one voxel, what you're doing is you compute the weighted average of the signed distance values that have seen that voxel from all views, right? So this D here, this is a depth value from 1 pixel minus the voxel's distance value. This is a weight that we compute. We'll get later to this weight, and we just normalize it by the weight. And then the weight, for every voxel, we also store a weight, and we sum up all the weights of all the depth values or signed distance values that have seen this voxel. But all you're doing is we're basically computing now an average signed distance value per voxel. This is what this formula is telling us, right? So D is the depth value di at x, but it's actually this depth value is relative to the voxel center, right? So this is the depth value minus the voxel center. This is the current value at that voxel. This is actually, it's not the depth value in the depth map, but it's the value from the depth map minus the voxel value, okay? Now let's talk about the weights quickly. The weight function here, wi, if you don't know what you're doing, just set w to 1, right? So every view will be weighted equally. But there's a couple of things you can do is you can say, well, you weight this thing depth-based. So you're saying the further away a point is, the more noise that point has. The closer a point is, the less noise it has. So you're trying to give closer points a higher weight and further away points a lower weight, right? And this is this wi. So one thing you can do here is you can have a function like this one. This is max w times 1 minus depth. This is 0 to 1 basically. It's a normalized depth range. And 1. So this is between 0 and 1. This is what this function ensures here. And this is what you can weight here. And then the isosurface is basically where d of x is equal to 0. That's very clear, and we can use our margin cubes to extract it. Now, I already mentioned this here. You can compute by saying, oh, we're computing basically a signed distance grid for every camera independently, and then we're averaging each of these grids. But what I mentioned, you can have a running average of these signed distance values. And this is what you're doing in practice, actually, right? So we're having the current signed distance value in a voxel, we're having the current weight in a voxel, then we're getting the new TSDF value of the current integration, and with the new weight of this current volume, and then you're normalizing respectively and you're updating the weight also, right? So this is just a running average. This here is the same thing than this, except this is computed incrementally. So, right, you're adding depth map by depth map, and you're doing integration depth frame by depth frame. Okay, so the WIX and the DIX are the cumulative signed distance and weight functions after integrating the ith depth image, right? Okay, and this method, what I just described, is a very, very famous method, this volumetric fusion. It was originally introduced by Curlis and Levoy. This is a paper you should actually have a look at. I don't have it in the reading homework right now, but actually add it to the reading homework. This is a very, very important, a very, very critical paper to understand for pretty much half of the lecture that is now to come. So this is really, really critical. But the idea of the surface integration is really straightforward, right? So we have a voxel. For one voxel, we have a distance value, we have a weight value. This is a TSDF value, this is a weight value. We can store a color too, but maybe let's ignore the color for now. The distance value is the sum here that we just had, right? This is this sum of the average of all the integrations. This is the weights. And now we can do this incrementally. And we can say, well, the updated d prime, or the di plus 1, is just this weighted average between what we had already in the voxel and what is yet to come. And the weight is also just updated. So I wanted to show you quickly how the C++ code of this looks like, because this is really straightforward to do. This is some code I wrote. So this is this integrate function. So this integrate function here, what it gets is, it gets as input an intrinsic matrix. So we need to know how to project stuff. We get our camera to well transformation. That's what we're getting from an ICP. And we're getting a depth image, which is where the depth values are stored. Okay. So what we want to do is, first of all, we compute basically which voxels are actually being valid projections into the current depth frame. Well, this is what this bounding box is doing, because we wanted to not have this massive 3D scene, but we only want to have stuff that is in the current camera frustum that is seen by this one depth value, right? And what happens here is we take every voxel in these 3 for loops that is in this frustum here, and within the bounds of this bounding box that we've just computed of this frustum. And what we're doing right now is, the first thing we're taking the voxel coordinate, which is I, J, K. This is our voxel 3D coordinate. We are projecting from voxel space to world space. And then we're going from world space to the current camera space. This is our ICP camera transformation, right? Then what we're doing is we are projecting. So this one is current. This is transforming the voxel into the current frame. This is giving you the floating point in camera space. Then we're projecting this point into the depth image. This is just with the scale and the depth. It takes the intrinsic. This is just an intrinsic camera transformation, what we're doing here. Then we have the point P. Well, we're converting this P to an integer value. Then we're checking, is it actually projected in the depth, in the bounds of the depth image, so we don't get a segmentation fault. Then we're looking up the depth value D at the location where this point projected. We're checking if there is actually a depth value, if it's within the min and max depth range. And now what we're doing is we're checking if the Z value is smaller than D, meaning that this is just a free space counter, so maybe we can ignore this one right now. But now we're computing the distance value, SDF, which is just the distance that we looked up in the depth map minus the Z map of the voxel in camera space, right? So this gives us the SDF value here. This is the current value from the current ray. We're checking what the truncation is, because we're now checking, is the SDF greater than minus truncation? So in other words, we're only doing this if we are greater than minus truncation, and I will show you in a second what this means. This is something we haven't talked about yet. But then we just do this weighted average. So we take the voxel value, the voxel's SDF value, we're computing this weight update, we're computing the SDF update based on the weights. We're computing the weight update, and that's basically it. But going back quickly, this SDF minus truncation is a thing we haven't discussed yet. So basically what this means is, if I'm going back here, it means we're only going to, let's say, -3 here. If the truncation is -3, we would only update to -3. And there's a reason for that, because you don't want to accidentally have duplicate surfaces if there's something coming on afterwards. Okay, so this is all this integration is. It's really straightforward, right? It's really, really basic how to implement this. Yeah, and that's basically the volumetric update step. That's it. That's the reconstruction part. Now, we have to do a little bit more stuff. We have already discussed how we can raycast a TSDF grid, right? In this case, we're casting a ray through the focal point of each pixel, traverse the rays along the TSDF grid, and finally, when we find an intersection here, we do a bilinear search. We can compute a normal by the gradient of the TSDF. We can raycast this whole thing. Or we can do a marching cubes from the TSDF grid and extracting a mesh out of it. Okay, so these are the things what we can do them with the reconstruction. So we have the raycasting and we have the marching cubes. Okay, but the integration we've just talked about. There's a few things I want to talk about, so a bit more for your understanding. There's one cool concept. Well, there's a few cool concepts of it. So first of all, what we're doing here is it's an approximative sign distance function. We're not actually doing a true sign distance value here. In fact, what we're doing is we are computing this projective integration, because that's what we're doing. So the less accurate, the further away you are from the surface, which makes sense. And the more accurate it gets, the more views you get. But what's important is the closer you are to the surface, around the surface, the sign distance values are pretty accurate. You could apply a real distance transform but you're missing some data and it's actually computationally costly. But I wanted to show you what this means here in practice. So basically, if you have a ray that is almost parallel to the surface, from this one ray, you would assign to this voxel a 6 here. This 6 is relative to this point here, right? Because you just computed the distance from that point to that current voxel here. And the downside here is that this is not a true distance here to this point, right? And that's basically a little wrong. But this is an extreme case. So this is some error in the computation of the distance here. But it's okay, because the closer you get to the surface, it's okay. Okay, there's a few interesting properties what we're getting here. So an interesting property is obviously, well, if you have 0, then you're on the surface, right? And if you go from minus to plus, then you're at 0 crossing. That means the surface must be somewhere in between. And there's another interesting thing, actually. And this is what I mentioned. So when we do volumetric integration here, I told you, well, if it's negative, it's behind the surface. And factually, that's not true. We are assuming it's behind the surface. But we don't know if behind the surface that there's another surface. So we don't know when that happens. So in practice, negative actually means it's unknown. So everything that is negative was behind an observation. We just don't know any better, right? Like, because there might be another surface behind it. But there's another aspect to it. Actually, when you are in front of it, then you know for sure it's free space. So if it's positive the sign, that means free space. And free space means, well, you have a depth value, right? And this depth value might have had a small error, so it might be a little noisy. But the further you go from this point to the camera, the more certain you are that nothing else comes there anymore. Because if there was another surface, this depth value would be different. So this free space concept is like super, super critical, actually. And this is called free space carving. This Curlis and Levoy paper, what I just mentioned, exploits that and explains it also quite well. This is something very similar to what we had been doing at the beginning when we talked about voxel carving. This concept here is kind of the same thing, like voxel carving with depth data. Yeah, but if you do this, you're getting actually quite nice reconstructions. So here again, here are some results from Curlis and Levoy. And there's also this Levoy et al. Paper. This is the digital Michelangelo's paper. So they basically took the laser scanners, they flew to Italy, they scanned the Michelangelo statues. This is David. This is the statue that Michelangelo did. and they reconstructed those ones with this volumetric fusion method. So they had these cyberware laser scanners, which I showed you at the very beginning of the lecture, and they're being reconstructed this way. Right, super cool research. I think this was very fundamental actually in this area. Okay, so at this point, like if you're looking at the year numbers, that's also interesting. These year numbers here is like 96, 2001, and so on. At this point, all of this stuff was like super slow, and this took forever to compute. But one thing I mentioned is you can actually do all of these things in real time, what I've just discussed. And the idea of doing this in real time is essentially a combination of an ICP and volumetric fusion. And this works something like this. It's like this pipeline here. So when you're getting a depth map as input, you get a depth map. You do some processing, you filter the depth map a bit. And what you're doing is, let's just say we're taking this depth map and we're integrating this depth map into a model. This is our volumetric fusion here. Okay, this is our model. Our model is being updated based on our volumetric fusion that we're doing right now. So now let's say we're getting another input depth map. What we're doing right now here is we're doing a camera pose estimation from this current depth map with respect to our model, just an ICP. From this ICP, we're getting a transformation that tells us now how to integrate, how to do a volumetric integration of this new depth map into our model again. And then we update our model accordingly, and then we get the third depth map. We align the third depth map again with respect to our model, get a camera pose, integrate the third frame, and continue, right? And this idea basically, it's doing two things at the same time, right? It's keeping this model around, and it's computing camera poses with respect to the current frame and the model. And then it's updating the model based on newly acquired data. And the reason when I started explaining this, I said at the beginning, when you get the first depth map, this model here is empty. Then what you do is you just initialize the camera pose with the identity and say, hey, this is our camera frame model right now, right? Okay, let's look at it again. Same idea, right? So we have a connected pose T0, T1, T-1, and so on, right? So we are scanning this Kinect. So what we're doing right now is here we capture the depth map, we filter it a bit, we have a bilateral filter, we track, we compute a camera pose of the current depth map with respect to the existing model. How do we do this? Well, we typically do a raycast. So we raycast the current model to get a depth map. From this raycast, we're getting the depth map, and we're comparing the current depth map to the raycasted depth map with an ICP. Then we get a transformation. Then we have a volumetric integration, and then we render the 3D surface. Again, right? So this is straightforward, right? Okay. So often what we're doing is, I mentioned this before, we're doing actually frame-to-model tracking here, rather than frame-to-frame tracking, because the normals of our raycasted model, they are a lot better. They're a lot smoother. You see that this is the normal map that we're getting on the import, and this is the normal we're getting from the raycasted TSDF here. Okay, and here's our reconstruction that we're getting, and that looks pretty good, I would say. Okay, and there's some prominent literature. I wanted you to have a look at this. Again, the Curlis and Levoy one, we already talked. This from Simon Rusinkiewicz, that's basically this efficient variance of ICP. That's pretty cool. He also had one of the first real-time frameworks there in 2002. And then there's a very popular method, which is Kinect Fusion by Richard Newcomb and Jerome Sadi et al. So these guys, they do this pipeline, what I just mentioned, to do this whole thing online. But let me show you a few videos here. So this is this first paper by Simon Rusinkiewicz. Right, so they use a very primitive structure light projector and camera here. And they're recording this. And this is their real-time version of this ICP here. So they're tracking it, and then they're updating the surface with volumetric fusion. Right, this was 2001, right? This is already early 2000s. It was already a while ago. Okay, this is the same version with Kinect Fusion. That's already a little later. This was like, I think 2011 or so. So let's have a look here. So they take a Kinect already. They have a much better sensor, of course. And this is how this looks like. Here, the input on the top left are the input depth frames. And you see the reconstructed surface normals here and the reconstructed geometry. Here you see another reconstruction. And so it's pretty cool, right? And this runs real time now. Okay, so I want to show a few things here. This is basically the pipeline of Kinect Fusion. Pipeline of Kinect Fusion is take a raw depth image, filter it a bit, do an ICP with respect to the current volume. The ICP is done with respect to the raycasted version of the current volume. Then you compare the raycasted depth with the current input depth map. You have a bunch of ICP outliers. Then you get a sixth of camera pulse. You integrate it to the current volume. You go to the next frame. Real straightforward. Yeah, I don't know. I'm very excited. I think this is really cool work. And since then, there have been a couple of interesting things how to expand this. And I wanted to quickly show a few of the examples. So this was in 2011, was this Kinect Fusion. This basically came out with the Kinect. And one problem they had is they basically ran out of memory very quickly. So they could only capture like one person basically. And the idea is you can extend this volume. There were a couple of extensions. There was like this extended Kinect Fusion, there was an hierarchical Kinect Fusion, and there was a version called voxel hashing. And I want to quickly go over these ones. Is basically how to adapt the data structures such that you can scan larger scenes. Because now it's a question of how to store all the sign distance fields and how to update them in real time. So this extended Kinect Fusion is kind of a cool idea. What they do is they use a moving volume. So what they do is basically they take the current input, it's just a small part here basically of the volume. And what they do is they just have a rolling volume. So they integrate on one side, and on the other side they run already marching cubes to extract the mesh, which is kind of cool. So basically you start on one side of the scene, you scan it, and then you move to the other side of the scene, but then in the meantime you have this rolling volume with a modular operator that reuses the same volume again, but when it reuses something, there's already been run on marching cubes and extracting that part of the data. So this is super easy. This is the simplest one to implement. Big downside, can't reintegrate, can't integrate in the previously obscene regions. This is kind of an issue, right? So this is probably the simplest one, but it's also a bit limited in terms of what you can do because you can't revisit parts of a scene you've already seen before. Another version of that is this hierarchical fusion. They basically use a hierarchical data structure where they have like a root volume, and then they have this kind of this octree structure where they do a spatial subdivision, and the SDF values live on the leaves here. But since this is a spatial subdivision, the leaves only exist around the surface. So the big plus here is it's super efficient storage, large spatial extent, and high local resolution and fast lookups. The downside is if you're getting new values in, you might have to update your tree structure, right? So insertion removal on a tree is not O of 1 anymore, obviously. It's log n, and if you do this log n on a GPU, that could actually cost you quite some performance, right? So the lookup is super fast, but the updates of the data structure here is a little bit slower. So the scanning might be a little bit slower. Okay, and then the last data structure I wanted to quickly talk about is spatial hashing. So spatial hashing is kind of straightforward. It's a really simple idea. So what you do is you store everything in a hash table, and every voxel, and you just have linearized entries of voxels that are stored in the hash table. And the idea is whenever you access an entry in a hash table, you compute a hash function, you'd feed in the x, y, and z coordinate of your current voxel as input, and based on this hash function here, you're going to get an entry in a linear array where that voxel is stored. So the actual storage is computed based on the hash function, right? So then you have basically two arrays. You have the voxels, you have the hash table, and the hash table just tells you, oh, this is my position, this is my current offset in my hash table, and this is my pointer that points where the data lives, like, right? And this is super easy to compute because this hash function is basically take the coordinate, multiply it with the prime number, XOR it with, with the other components respectively, and modulo in. This is like on a GPU, that's like nothing. Like there's no memory access involved. This is just computing O of 1. And here the idea is that the updates are really, really fast in this voxel hashing data structure. So the idea is you can have very large spatial extents, high local resolutions, and insertion and removal compared to an octree, what we've seen before, is actually O of 1 rather than log n. And the big thing is basically you can run this on arbitrary large scenes, and you can also stream stuff from a hash table out very easily. The only drawback of the hashing data structure is that the raycast is not that fast anymore. So for instance, if you're going back quickly, this hierarchical fusion, here the data structure is super good in terms of the lookup. The lookup here is basically log n traverse the tree, and you can skip a lot of free space. Here, the lookup is a little slower because the lookup means you have to go voxel by voxel through in order to find the zero crossing. So the raycasting operator in this Kinect Fusion pipeline is a little bit slower. But the insertion and the removal is O of 1, and this is what you really need in this volumetric fusion stuff. This has to be super fast. There's a few tricks and details how to get it even faster on the GPU. Rather than storing it on a per voxel basis, you're storing it in voxel blocks of 8 cube blocks, and so on. But yeah, so this was done, this paper was done in 2013, I think. And the idea there is basically that you see like the whole stuff runs in a few milliseconds, and you're super fast here. So if you're interested in data structures, you should be interested in data structures. I would highly recommend try to understand the concept of volumetric spatial hashing, such as in voxel hashing, and or sparse octrees, such as in this hierarchical fusion paper. And I think that would be pretty cool to look up. And if you look at it, this is one of the results that the voxel hashing paper has. You can actually scan now pretty large environments with it, right? And this, I think, is pretty cool. I don't know. I was very excited when we got these results. All right, so you see this is a big library in Cambridge, actually. And you get like this large reconstruction here of this whole building or of this whole floor. And you can do it all interactively. You can revisit it and so on. And I think this is kind of cool. So up to date, I would say that the spatial hashing data structures are still widely used. I mean, for this kind of reconstructions, I would say it's probably still state of the art. There's a few variations to it you can do, but this one works extremely well because the access is very, very fast. Okay. There's a few other representations I wanted to talk about. There's also things as point-based fusions. So rather than storing it in a grid, you can just go ahead and store it in voxel instead of voxels, you can use servals. A serval is basically a point plus a normal plus a radius. The advantage is this is unstructured, so doing updates is also relatively cheap. The rendering you have to do via splatting. The graphics pipeline can do that, so you splat basically like small like circles or ellipsoids. So the unstructured storage means there's a large extent and high resolution. It's a little easier if you want to extend it later to dynamics. Also, this is still not, it's still even up to date. It's not fully solved yet. And the surface quality is slightly less than the volumetric sign distance fields. So yeah, to give you maybe an example, it looks something like this here. This is like serval-based representation. This is TSDF-based representation. This is kind of a comparison here side by side. So the TSDF in a grid has a higher quality. This is why probably people mostly use the TSDF fusion today. Okay, so there's a few things I wanted to talk about. So reconstruction-wise, I think the voxel hashing data structure is very cool. That works. That's what everybody uses, I think, today. What is not so cool yet is if you're running, for instance, voxel hashing on an office scene, you're getting results like these ones. And this is a problem we haven't really talked about yet. Because in all of these methods that I've just shown you, is you basically taking depth frames as input, and you're aligning these depth frames to the respective target views. Sorry, you're taking the depth frames, you're aligning it to the model, and you're doing this frame by frame, right? So you're getting your frame, aligning it, getting your frame, aligning it, getting your frame, aligning it. So the problem with that is there's drift, and due to this drift, you're making a small error every time you're adding a new frame. So locally, the ICP works great, but globally, the ICP accumulates the errors, and because of that, you're going to get these loop closure problems, which is basically that kind of stuff here. And that's an issue. That's something that has to be addressed. And if you remember, we have talked about this already, because in a sense, bundle adjustment addresses this perfectly, right? If you have all frames given in advance, you're doing this global feature matching, you can solve for the global pulses. Sadly, that's not what ICP is doing. ICP is doing this very locally. But let's see, there's a couple of ideas how to do this, and I wanted to show a few ideas. So one question is, how do we even update the surface? This is Elastic Fusion, which is a really cool work. And what that is doing, it's using a point-based representations based on circles. And the idea is, with the circles, you can update it much better. You still do frame-to-model tracking, but you detect loop closures by localization. And if you're detecting a loop closure through localization, you're just doing a non-rigid warp to close these loops. And this is what happens here, right? So they do a reconstruction here. And then here was the loop closure detected. Now they detect it. And then they non-rigidly warp the Serval-based points in order to get the final alignment here. Okay. They have another one here I wanted to show. Same idea, right? So they have this point-based Serval reconstruction. So the point-based Serval reconstruction is a little easier to update in a sense there, because they can just non-rigidly warp the outputs accordingly. And they achieve pretty good results, right? Okay, now this is working on this point-based, on the Serval-based representation, which is actually not too bad for this kind of task, but the quality is not that high. Now I wanted to show you a few more things what has done been afterwards. And one very popular method is actually this bundle fusion work. So the idea of bundle fusion is you're treating it more as a bundle adjustment problem, right? So the idea is you have a set of RGBD frames, you do correspondence search based on SIFT matches, you do a global pulse optimization, and then you do a dynamic update of the surface. So a lot of these components we have already seen. A lot of these components you have already seen. So bundle adjustment has two terms. It has a sparse feature term and a dense feature term. The sparse feature term is essentially RGBD bundling, right? So you're using SIFT matches between, so you're taking frame pairs, you're finding correspondences between those frame pairs. And each frame has a transformation T. And then you're having the correspondences, PIK and PJK, right? You're finding these based on SIFT matches. You're globally optimizing this with Lemberg-Marquardt, Gauss-Newton, or whatsoever. And then bundle fusion has these dense terms. We have seen those ones also. This was the dense RGB term. And in this case, we have here, again, I'm going to go quickly through it. You have a point in the current frame. You look up, you take this point, transform it to the canonical frame. You're transferring it to the other frame. You're projecting it to the other frame. You're looking up the depth value. You're projecting this depth value back to camera space. And you're projecting this looked up back projected value back to canonical space, and then you're projecting it back to the previous frame, and then this value, this point you have back projected now, has to be the same than the original PK. And this is also a point to plane. This is why the normal is here. And this is this dense depth term. Now you should actually fully understand this dense depth term. Like now, there's no excuses anymore. You should understand all of these different variables and what this term is doing. And this dense depth term is basically now saying, well, you have a bunch of these correspondences, right? And you're having this dense ICP term. Same thing you can do for the color values. You can take a color value, so you take the color value in the current frame, you take a point in the current frame, project in the color space, look up the gradient there of the color, and you're comparing it with, you're taking the same point, projecting it to the other frame, look up the color value there, and look up and based on the projection, you look up the color value, and then you take the distance here. And then you basically do the same thing in color space between those two frames, you're computing the distance. And that is basically from bundle fusion, this is the global pulse optimization part, right? If I'm going back quickly here, it has these two terms, sparse and dense, and it's actually jointly optimizing, well, it's first optimizing the sparse one and then jointly optimizing sparse and dense. And that gives you pretty good pulses, and this is implemented in a very efficient Gauss-Newton solver actually on the GPU. This can be parallelized. It takes a lot of time to implement it, but it can be done very fast. And now there's another trick what bundle fusion is doing. Now, because you want to still do this incrementally, you want to basically use this volumetric update, volumetric integration function. And we've talked about this. One thing you do this is you do this incrementally, right? So you can say, oh, we are basically taking the current depth, the current weights, we're updating it, and then we're having the current weight and we're updating that one too. The interesting thing is, let's just assume hypothetically, we integrated a depth frame with the current pose. But later on, based on the global pulse optimization, we realized, oh no, darn, our pulse in the past was slightly wrong, we have to fix it. What we can do actually here is we can do a thing called Volumetric D Integration. And look at the term here, right? It's very straightforward. It's like this running average. It's just removing a frame. So bundle fusion can remove a current frame from this data structure and then reintegrating it with a new pose. In practice, that works like this. So let's say this is a current frame. We're getting a new frame, and our pose is slightly wrong, right? So this is integrated with the wrong pose. You see this doesn't quite align here, this frame, right? This is like kind of broken. What we can do is we can de-integrate this frame and then reintegrate it with the updated pose, right? So here now the new pose looks better, right? And because of that, bundle fusion runs in real time and gets global pose correction with loop closure and avoids drift and stuff like this. So practice that looks like this. I want to show you this video. Oh, yeah, this is me while I was still at Stanford. Actually, it's kind of funny. So we're holding here. This is an RGBD sensor. It's an occipital sensor. It's basically a mobile Kinect. The RGBD frames are being streamed to the GPU of the computer from the iPad. And now here you see the top-down reconstruction at the bottom right. Okay, now we're seeing this problem that here we have a loop closure issue, right? So this one is not quite right. Now, what's happening here is when you continue, bundle fusion detects this in the pulse optimization part, and it's reintegrating all the frames around it after the pulse optimization kicks in, and now we have the loop closure fixed. Now if you're looking, well, now it's a really rectangular room, right? And the pulses are globally aligned. Here's another example of this. Same thing. Now we're coming around. You see there's some drift. And now it fixed the reconstruction once it updates it. Okay. The interesting thing is this can also do relocalization. So you can actually occlude the sensor. And then it's refining the tracking, basically. So it has like this relocalization module, basically. And then you can just go ahead and continue scanning. Same idea here, right? You could just go to a different place. And then you can redo the scanning. If you're looking at it, Bundle Fusion gives you pretty good results. So this is a copy room that's reconstructed here. And if you're looking closely in, the surfaces here are actually pretty cool already. Right? So these are the reconstruction results you're getting with Bundle Fusion. I think that's kind of cool. We were super excited when we got these kind of results, and yeah, that's kind of nice. Okay, few other things. What I wanted to quickly mention. Some of these things are actually implemented already in commercial devices. So, so if you're doing this on a commercial device, many people don't just do ICP the way we said. Many people actually using ICP in combination with an IMU, right? So they're using like the accelerometer and gyroscope to help the pulse estimation of the ICP. And there's a couple of papers that combine ICP and IMUs, and this works quite well. And these kind of commercial solutions that people have been doing is, for instance, Google Tango or Microsoft HoloLens. They implemented visual odometry with a combination of an IMU. So in practice, when you're doing this as a commercial tool, I just wanted to mention that people not just using visual tracking, but they're using IMUs as well. And there's like really cool devices. So I mean, sadly Google discontinued it, but I was a big fan of this Tango phone when they had it, because they basically had a time of flight camera basically in the phone. This was the time of flight camera here. Sorry, this is the time of flight camera. This is the global shutter camera with the fisheye that was responsible for the tracking here. And they basically had a depth sensor on the phone, and this was kind of cool. And I thought, yeah, this is now we're gonna have like depth sensors in every phone. So they discontinued the project, but I should say the new iPhones actually has a LiDAR sensor in it right now. So most phones actually, well, the newer high-end versions, they actually do have the depth sensors in it. So that's kind of cool. But yeah, this is still a fun fact. I'm actually still using one of these Tango phones because for the you see here the sensors here on the back, just for the nostalgia effect. So the phones are like super unstable and they crash all the time, overheat, and you really know they're developer models, but they have a cool depth sensor in it and they have this cool visual inertial tracking in it. And I think that's kind of nice and maybe worth the effort for a researcher. All right. So yeah, if you want to look up some stuff like Google a bit Google Tango and Microsoft HoloLens, because they have really rock solid tracking, I think, and that's I think pretty impressive what people have been doing there. Okay, with that I'm at the end of the lecture. Few small administrative things, couple of things I mentioned already. I have some reading homework as usual. I want you to look at this Love paper. That's the paper with the linearized version of the point-to-plane ICP. I want you to have a look at the Rusinkiewicz paper, the symmetric objective function for the ICP. I'm not saying the symmetric objective function is the way to go, but by reading this paper, you will understand the variations of the point-plane ICP a bit better. And the last thing I would like you to do is read up on SVD and covariance matrices. I noticed this recently that people don't know what an ICP, don't know what an SVD is, because when I tell you, oh, like an ICP point to plane, you linearize it, you get a 6x6 matrix, 6x6 system, use an SVD to solve it. And if people don't know what an SVD is and how to solve this kind of stuff, that's a really big issue. So at this point, you need to know what an SVD is. You need to know how it's computed. You need to know what a singular value is. You need to know what the difference to an eigenvalue is and stuff like that, right? You also need to know what a covariance matrix is, because in Progrust you compute the covariance matrix of the correspondences, right? And then you're computing an SVD out of the covariance matrix, and that gives you the rotation matrix. So that stuff you just gotta know. And I know that this has been done in math intro lectures, but I want you to look it up again because you cannot solve any of this stuff without this basic math. Okay, yeah, and then next week, now we've done a bit of rigid surface reconstruction. We're gonna go to non-rigids and see where we can go. So thanks a lot for tuning in. See you all next week. Bye-bye.